This video tutorial is the first part of a four-part series of discussions on test questions in electrostatics. Electrostatics is one field in physics that deals with the study of charges at rest. Studying electricity simply requires us to know the structure of an atom. Okay? And the Rutherford's model or the nuclear model of an atom is sufficient for us to be able to understand, okay, electricity. And the three fundamental particles, such as electrons, protons, and neutrons, are just the kinds of particles that we need to know. So in the table, we take note of the mass, of course, the location, and the charge of each of these particles. For instance, for the electron, which is, as we know, is a negatively charged particle, has a mass of 9.11 raised to the negative 28 grams, and it's located around the nucleus in an electron cloud. For the positively charged particle, or the proton, okay, the mass is 1.67 raised to the negative 24 grams, and it is located exactly at the nucleus. And lastly, for the neutral particle with zero charge and a mass of 1.67 times 10 to the negative 24 grams, also is located at the nucleus. You will notice that the proton and the neutron almost have the same atomic mass. There are two types of charges: the positive charge and the negative charge. And the SI unit of electric charge is the Coulomb, denoted by capital C. The magnitude of the charge on an electron or a proton is 1.60 times 10 to the negative 19 Coulomb. So it depends if you're talking about the charge of an electron, which should be negative 1.60 times 10 to the negative 19 Coulomb. But if you're referring to a charge of a proton, then it is positive 1.60 times 10 to the negative 19 coulombs. Alright, we also emphasize that the charge on any object, whether it is positive or negative, is always quantized, in the sense that the charge consists of an integer number of protons or electrons. Integer number means it's always expressed in a whole number. Okay, we cannot have a decimal or a fraction of an electron or a proton. And 1 coulomb of charge is exactly equal to 6.25 raised to the 18 electrons or protons. Okay, this number of particles or charged particles of 1 coulomb, if you will try to check, is just actually the reciprocal of the value of or the magnitude of the charge of an electron or a proton. For example, 1.60 times 10 to the negative 19 coulomb. If you're going to get the reciprocal value for this number, you will get the equivalent number of electrons or protons in 1 coulomb, which is 6.25 times 10 to the 18 electrons or protons. I hope that is clear. We will be in most cases of our problem solving, we will be using these two constants. All right, we also emphasize the law of conservation of electric charge, which simply states that the net electric charge or total electric charge of an insulated system always remains constant during any process. Okay, one of the questions that we're going to discuss later will actually apply this law of conservation of electric charge. You must be familiar with the saying, like charges repel and opposite charges attract. Well, actually, this statement is a fundamental law in electrostatics. We may also add to that charged bodies, whether it is positive or negative, actually attract and never repel a neutral or an uncharged body. Let's now talk about our first example. A neutral dielectric has added to it 12.5 times 10 to the 18th electrons. What is its charge in coulombs? Alright, so we are talking about a kind of insulator in electronics. We call this a dielectric. And initially it is neutral or no charge, zero charge. Then 12.5 raised to the 18 electrons are added or transferred to this neutral dielectric. So what's going to be the net charge of the dielectric if 12.5 raised to the 18 electrons will be transferred to the dielectric? Okay, we want the answer in coulombs. All right, so you will notice that 12.5 raised to the 18 electrons is just twice the value of the number of electrons in 1 coulomb of charge. Therefore, uh, our answer is that the net charge of this dielectric will be negative 2 coulombs. That is simply because, okay, we just doubled, the number of electrons that's transferred to the dielectric. If 1 coulomb has 6.25 raised to the 18 electrons, therefore 12.5 times 10 to the 18 is just twice that value of 1 coulomb in terms of the number of electrons. All right, let's go to number 2. A dielectric, similar to what's mentioned in number 1, has a positive charge of 12.5, okay, times 10 to the 18 protons. What is its charge in coulombs? So, unlike in example 1, this time we are describing a dielectric having a positive charge of 12.5 raised to the 18 protons. That means that instead of adding, that number of electrons to the dielectric, what was done is you're going to remove, remove that number of electrons. Okay, removing electrons from a neutral atom will make it positively charged. So when you say 12.8 times 10 to the 18 protons, all right, some people would normally say that 12.5 times 10 to the 18 protons have been transferred to the dielectric. Well, in fact, there is something wrong with that notion because, as we all know, protons can never be taken away or removed just like that from the nucleus. So during ordinary processes such as chemical reactions, the protons, which are stable in the nucleus, cannot be easily removed from the protons. So they do not participate in the process of chemical reactions such as transfer or sharing of electrons. What is correct is to say that this number of electrons have been removed, all right, from the dielectric. That is more conceptually correct. Okay, removing these electrons, that number of electrons will make the dielectric positively charged. And that is what's being asked. What is its charge in coulombs? All right. Another term of describing this, whenever electrons are removed from a material such as a dielectric, it therefore becomes deficient of electrons. All right. So our answer is that since 12.5 times 10 to the 18, all right, electrons have been removed. So that's exactly the same number of electrons that were added in example 1, that were added to the dielectric. But this time in number 2, we're talking about that number of electrons being removed from the dielectric, making it positively charged. All right, so our answer to number 2 is just the same as our answer in number 1, except that it has a positive charge of 2 coulombs. We now have example number 3. A dielectric with a charge of positive 2 coulombs has 12.5 raised to the 18 electrons added. Question is, what is its charge then? So, the dielectric is already charged initially, amounting to positive 2 coulombs. And then you are going to add that number of electrons, 12.5 raised to the 18 electrons, which is twice the number of electrons for 1 coulomb, isn't it? So, because of that, what will happen to the net charge of this dielectric? All right, the answer is it's going to become neutral, because the 2 coulomb of negative charges added by the electrons will cancel the 2 coulomb of positive charge it originally has, making the dielectric neutral or uncharged. So the answer is the net charge Q is 0. Number 4. A piece of plastic has a net charge of positive 2 microcoulomb. How many more protons than electrons does this piece of plastic have? Okay, so you are given the net charge of the plastic, which is positive 2 microcoulomb. First, we need to convert microcoulomb to coulombs. All right, and that is shown in this simple computation. So positive 2 microcoulombs is just equal to positive 2.00 raised to the negative 6 coulombs. And then our question is asking for the number of protons in excess to the number of electrons. So we will let capital N, okay, as the number of excess protons. Then we just multiply, all right, the given charge of positive 2.00 raised to the negative 6 coulomb. We just multiply it by the equivalent number of protons in 1 coulomb. All right, in 1 coulomb, there are 6.25 raised to the 18 protons. So you will notice that the unit coulomb will cancel out in this simple equation. So we will get the answer for the number of excess protons, capital N, which is 1.25 times 10 to the 13 protons. All right, we just multiplied 6.25 times 2, all right, and then we just add the exponents, and this is our final result. Our example number 5 is, what is the charge on a 1 kilogram of protons? All right, so our solution goes like this. The mass of a proton, as given earlier, is equal to 1.67 times 10 to the negative 27 kilograms. Okay, so since we're looking for the charge, we will first determine the number of protons that is found in 1 kilogram. Okay, 1 kilogram of protons, what is the number of protons? Okay, so let that be capital N. All right, that is the meaning of this. How many protons are there in 1 kilogram? That's the meaning of N over 1 kilogram. All right, and we equate this to, for every proton or 1 proton, the equivalent mass is 1.67 times 10 to the negative 27 kilogram. All right, so this equation is actually a ratio and proportion. If you're familiar with that, no? Ratio and proportion. Uh, so if you're going to simplify, the unit kilogram will simply cancels out, or will cancel out. And that leaves us the number of protons, uh, which is equal to 6.0 raised to the 26, or 6.0 times 10 to the 26 protons. But since what is being asked is the charge, we will now convert this number of protons, Q, into the amount of charge, which is symbolized by capital Q. And we know that in 1 proton, the charge is 1.6 times 10 to the negative 19 Coulomb. All right, that is the charge of a proton. In the case of an electron, it's the same value but with a negative sign, negative 1.6 times 10 to the negative 19 Coulomb. All right, so again, in this simple equation, the unit proton cancels out, and we will get as our unit for the charge that we are looking for, which is Coulomb. And the product of 6 raised to the 26 multiplied by 1.6 raised to the negative 19 is a value that is 9.6 raised to the 7th. But since we're talking about positive charge, okay, protons is what we are referring to, then it is with a positive sign. This is now our last example, number 6. 4 identical metallic objects carry the following charges. The first one has 1.6, positive 1.6 microcoulomb. Okay. The second object has positive 6.2 microcoulomb. The third has negative 4.8 microcoulomb. And the fourth object has a charge of negative 9.4 microcoulomb. Now, the objects are brought simultaneously into contact so that each touches the others. All right? So this is one process of what we call charging by contact. There is a direct physical contact, okay, among these 4 metallic objects. So what's going to happen? All right. after which, after the physical contact of the four metallic objects, they are to be separated. All right? And then first question asked is, what is the final charge on each object? And the second question, how many electrons or protons make up the final charge on each object? So this last example will actually illustrate the meaning of the law of conservation of charge, which was stated earlier as the number of charge before any process takes place will just be equal to the number of charge after the occurrence of whatever process. Okay? And in this case, the process that we're talking about is a simple conduction method of charging. Okay, so first, we have to find the final charge on the object. But before we can do that, this is what we will first have to do. We will get the total. All right? We get the total charge by adding all the given charges. Okay? Some are positively charged, some are negatively charged. So it's like we just add them algebraically. Okay? Before we convert into Coulomb, just add them directly first, okay, in their original unit microcoulomb. So positive 1.6 microcoulomb plus 6.2 microcoulomb minus 4.8 microcoulomb minus 9.4 microcoulomb, it will give us a total charge of negative 6.4 microcoulomb, which when converted, of course, to Coulomb will give you negative 6.4 raised to the negative 6 Coulomb. Okay, that is the total charge for the four metallic objects, right? Before they were made to touch, okay, with each other. So after touching, and then they were separated, we are asked to find what do you think will be the charge of each, all right? After they are separated, what will be the individual charge of each? So what happens is we will just divide the total charge by the number of objects or metallic objects equally divided, because we said according to the problem they are identical metallic objects. So naturally, okay, when they are separated, each charge should get an equal amount of charge, which is negative 6.4 times 10 to the negative 6 Coulomb divided by 4 will give us negative 1.6 times 10 to the negative 6 Coulomb. So this is the charge, final charge on each metal after they have been separated. Okay, and moving on to the second question, how many electrons, or should it be protons, will make up the final charge on each object? All right. Since our result for our answer in letter A indicates that the charge is negative, then we are talking about excess of electrons for each metallic object. All right. We are sure that it's excess of electrons, okay, that we're talking about, and not protons. That is because of the negative sign of our final Q, the answer to letter A. So what do we do to get the number of electrons? Again, we go back to our usual, okay, procedure of finding the number of particles or electrons. Okay, the given charge Q on each will just be multiplied to the number of electrons, okay, there are in a charge of -1 Coulomb. All right, so that would mean we just multiply -1.6 raised to the -6 times 6.25 raised to the 18, and then divide that by 1, of course, or -1, and we will get for our number of excess electrons in each metallic object amounting to 1.0 times 10 to the 13 electrons. Okay, so this is an illustration of the law of conservation of charges. That will be all for now. This is just part 1 of our tutorial in this topic on electrostatics. The second part, we'll be talking about electrostatic force. All right, so I hope you will uh, see each other. We'll see each other in the next tutorial. Thank you for your indulgence.